Hey everyone! So today we're going to be talking about stellar evolution, or basically in layman's terms, the life cycle of a star. Okay, so basically we're going to be talking about the journey of a star from birth to death. Okay, so we're going to be talking about a couple of different things. We'll focus first on the actual life cycle from, a young star to a middle-aged star to an older star, and then we'll focus a little bit more on the death of a star. So maybe I'll split the two, with the life cycle being the first video and the death of a star being the second video, but we'll figure that out. So there's two things that you need to be aware of. Well, there's two types of stars that you need to be aware of, and the first one is called a low mass star. Okay, so there's two types of stars. Okay, so we've got the first one is a low mass star, and then we've got massive stars. Okay, these are the two types of stars that we're going to be focusing on here. And the reason that you need to make this distinction between the two is because their life cycles, while they are similar, there is a little bit of a difference between them. Okay, so we're going to start by talking about low mass stars, and then we'll talk about massive stars, and you'll see a little bit of a difference. Okay, so to start, let's focus on low mass stars. Okay? So we'll begin. I'm going to erase this bit. So we're talking low mass stars to begin with. Okay? So the first thing is a low mass star will begin as a stellar nebula. Okay, you might have heard the word nebula before. If not, that's okay. Basically, a nebula is a big cloud of dust and gas, basically the raw materials that you need to create a star. Okay, so it'll have lots of hydrogen, lots of helium, and it'll have some amount of other stuff as well, things that could form into planets, for instance. So the elements that you would commonly see in planets, you might also find in this type of a nebula. Now, the nebula itself usually comes from the death of a previous star. So it's basically star stuff that's been spewed out into space, and then the process restarts. So the first step is a stellar nebula. So you have clouds of gas and dust, and at some point the gas and dust becomes a little bit more dense in a certain region. All right, so let's say you've got you've got your cloud over here, and you've got a cloud over here, and a third cloud over here. So you just got all this gas and dust kind of all over the place, but somewhere in the middle of one of these, the gas and dust is a little bit denser. Either there's just more, hydrogen and helium there, or there's more heavy stuff. There are more denser atoms in that space. And basically what happens is, if you have a super dense region in one part of the gas cloud and less dense regions in the other parts, then basically what you get is that the gravity of the denser region starts to pull the rest of the material inwards. Okay, so basically you have this cloud of gas and dust, and it all starts to compress under its own gravity until you get something like a protostar. A protostar is just like the baby version of a star. Okay, so you get a brand new sun or sun-like star, and then all this other less dense material around it. Okay, so basically you wind up with a stellar nebula that compresses up until the point where the gas and dust compress to a point where nuclear fusion starts to take place. So basically, fusion of elements is when you have two lighter elements, like let's say two hydrogen atoms, and due to the heat and pressure, they collide with each other and form one helium atom. Alright, so you've got two hydrogen atoms, they collide with each other, they form a helium atom, and they release some energy. Okay, that's the fusion that powers stars. The light and heat that we get from the sun comes from this type of a process. Okay, now it's not always hydrogen to helium. Once you run out of all the hydrogen, you move on to heavier stuff, which we're going to talk about in just a sec. But basically you have the stellar nebula, and then once that fusion process begins, you have a star, and then you've got all this material around it, all the rest of that less dense material that isn't making up the star, just in orbit around the star. You have this disk. And basically that is the stuff that forms planets. So when you see a solar system, you'll have a star that had a bunch of this leftover material, and all of that leftover material went through the same process of it's a little bit denser here, things start to get gravitationally attracted, they collide, and boom, you have planets. Alright, the difference between planets and stars, like gas giant planets like Jupiter, is that they're not heavy enough, they're not massive enough to have this fusion process occur, which is the difference between Jupiter, which is made out of the same stuff as the sun, and the sun itself. The sun is massive enough for this process to take place, Jupiter is not. Okay? So now you have a low mass star living its life. It might have planets, it might have no planets, and then after a period of time, so it's got a whole bunch of hydrogen inside, and it's fusing it all into helium, but if it only has a limited supply of hydrogen, then eventually it's going to run out. So once it starts to run out of hydrogen, it has to start using the helium, all the helium that it's made, and some of the helium that might have been there since the star formed, and it's going to have to start taking two helium atoms and fusing them together into progressively heavier and heavier elements. Now it doesn't go element by element on the periodic table. It doesn't go hydrogen, helium, lithium, beryllium. It kind of jumps a few and goes to kind of like around where carbon, nitrogen, oxygen, where those kinds of elements are. That's sort of the next big jump. But basically the idea is you start with super light elements, hydrogen and helium, and you fuse them into progressively heavier elements. So hydrogen and helium are really light, then carbon, nitrogen, and oxygen are heavier, and then you get to even heavier elements. And basically, you go through this long chain reaction. You fuse into carbon and neon and all of these different elements, and then eventually you get two atoms that collide with each other, and they form iron. This Fe is iron. Okay? Now the thing with iron is it starts to, this is kind of the beginning of the end for a star. So as it starts to run out of its lighter elements, the star actually grows in size, and it goes from being a low mass star, I didn't write this in yet, so we've got a stellar nebula goes to a low mass star, which is undergoing fusion, and then from a low mass star, it turns into a red giant. Right, it turns into a red giant star. So basically, as it gets older and it starts to burn through more and more of this energy, it grows and it starts to turn redder than it used to be, at least. So our sun is considered a yellow dwarf star. As it gets older, it'll look progressively redder. And with stars, red, the color of the star indicates the temperature of the star, but it's kind of backwards from what you might picture, because with humans and with, like taps in the bathroom, red means hot and blue means cold. Stars are a little bit backwards. Blue stars are the hottest, red stars are the coldest. So red giant stars are colder than yellow stars, and yellow stars are colder than blue stars. Okay, so now you have a red giant star, so you went from a stellar nebula, which was just kind of that cloud of gas and dust, which became a star, and then over several billion years that star grew into a larger and redder star, which is called a red giant. So that's where we're at now. Now, back to the thing about iron. Once you have a bunch of iron in the middle, in the core of the star, the problem with iron is that either the star is not heavy enough to fuse it into something more, or it's that if it can fuse iron into something else, it takes so much energy that it's just not worth the star's time. The star is actually losing energy by trying to fuse iron into something else. So once iron starts to build up in the core of a star, this is kind of the beginning of the end for a star. Even really, really massive stars can't really get past this. And so basically what happens is the iron can't fuse into anything else, which means that output of energy slows down. All right? Now that output of energy is what is keeping the star the size that it is. It's got such a strong gravitational pull that it would collapse under its own weight if it weren't for this output of energy. So what happens? This energy stops or gradually slows down, and then eventually the gravitational pull of the star, that's just the weight of the star, overcomes this outward pressure from the fusion that's happening in the core, because the fusion is coming to a stop. And basically what happens is the whole star compresses in on itself. The whole star just collapses, and usually for smaller stars it's not as kind of magnificent as for larger stars, but basically the outer layers of the star get blown off into space, and the core of the star gets compressed into what we call a white dwarf. A white dwarf. Okay, so you have basically, this is the death of a star. The white dwarf is basically the end product. There is a hypothesized thing after that, we'll get into it in a little bit. But basically, yeah, so when the star is about to die, its core collapses, the outer layers of the star get blown off into space, and that remaining core is a white dwarf. And that white dwarf will be quite small. So you have the star is like, no, let's say like the sun is 100 times wider than Earth. So it has a volume 1,000,000 times that of Earth's. But a white dwarf would maybe be the size of Earth, or not that much larger. So it gets really, really compressed, and it contains a sizable chunk of the star's mass because the core is really dense and really heavy. So it's about the size of Earth, but it'll be much, much more massive than Earth. So you could still find planets in orbit around a white dwarf as long as they survived this explosion. So that's low-mass stars. So basically it goes stellar nebula to a low-mass star to a red giant to a white dwarf. And then the last bit after that is that it goes from a white dwarf, I haven't planned out my writing very well, but it goes from a white dwarf to a black dwarf. And basically a black dwarf is just a white dwarf that has cooled down. So a white dwarf itself will still be really hot like a star, and so it's still emitting light and heat. A black dwarf is basically a white dwarf that's lost all of its heat. So that white dwarf isn't generating any heat, it's just leftover heat from the star while it was alive. So it's not creating more heat, it just is really hot, and when it cools down it becomes a black dwarf. Now this process takes so long that we haven't actually seen any black dwarfs yet, because it's supposed to take like billions if not trillions of years for a white dwarf to cool down into a black dwarf, and the universe hasn't been around long enough for this process to happen yet. So this one is just hypothesized. It's a pretty good guess, but so far there's no evidence of one directly. Now massive stars are very similar, and we're going to talk about that in the next video in more detail. But basically there aren't that many differences to this in the first half, so it'll still start the same way. So massive stars Massive stars begin their journey in the same way with the stellar nebula. Okay, now in the next video we'll pick up on basically this second step onwards, because from here on it's a little bit different, but you'll see that the general idea is the same. So we'll pick up on massive stars in the next video.